Welcome. In this session, we'll be looking at the different kinds of decisions that we can make by understanding the samples themselves. And this is a very important concept before we get to hypothesis testing, which will be our next topic. The learning objectives here is to understand when we can ask a question of a sample, how confident are we that the sample reflects its population? How large of a sample might you need within some range of values to represent that population? And how can I know about the population with a small sample? We'll try to address each of these. We're generally overconfident in our opinions and our impressions and judgments. This is a quote by Daniel Kahneman, one of the researchers that looks at social influence, especially when making decisions with data. He has an excellent set of resources on this kind of topic, and we'll talk about how it's related to some of the things we're going to look at today. When we look at a population versus a sample, we are mindful that the population is supposed to be represented in the sample that we're drawing from it. In fact, this is really what we're trying to do with inferential statistics, is answer a question by utilizing the data we do have in our sample to help us understand the population. When we see the results, they are only estimates of values that are actually in that population, and because of that, we have to make some adjustments to some of those values as we're trying to work with them in some of the statistics that we're running. An appropriate sampling is going to allow us a high degree of confidence actually in interpreting this population based on our sample, and that's good news. Parameters are the measures that we refer to in the population. So the mean of a population is referred to as mu. This is the symbol for the population's variance and standard deviation, and also proportion. When we look at a random sample from that population, we have to change the way we refer to those statistics. We call these point estimates of the population, and they are things like the mean, the variance, the standard deviation, proportion, and they have slightly different notation if you're looking at them like in a textbook. So we'll be mindful of that as we're going forward, but we're trying to understand the sample. The sample is telling us something about the population, and that's what we're trying to utilize the point estimates for. The central limit theorem is super important. This is probably the backbone of statistics, really, when you understand how important this is. Without this, I think we would be very limited in our ability to make sense of populations. When we select a large random sample, which might not be as large as some think, really if you have a sample of about 30 or so from any population, the means from those samples will be distributed normally around the population's mean. And that's very important because we typically want to make some kind of interpretation of a population's mean. Regardless of the distribution of the population in reality, it will actually always appear normal, or just about always. Even with very skewed populations, if we utilize sample sizes of about 50, it tends to normal out, and I will show you that in a demonstration in just a moment. The mean of a large, properly drawn sample, properly drawn meaning randomly, will resemble the population from which it's drawn. And so we have variation from sample to sample, but not likely massively, so that they do in fact represent the underlying population. Here is a description, illustration of 10,000 samples, size 5. So we've taken a bunch of samples of size 5 from these two populations of some kind of variable. This is just theoretical. So this might be IQs, for example. We've looked at that a number of times in the class, how IQs are typically normally distributed around a mean 100 and a standard deviation of 15. This might be something like maybe weights of the population, or something that might be skewed, where there's very few people that are super heavy. Most people are going to be, lower, and it really can be anything that we could imagine. But the point is that as we draw from both of these populations 10,000 samples of 5, you can see what's happening with their distributions. What does this remind you of? They're pretty normal. obviously it's probably not a surprise that by drawing 10,000 samples of 5, the normal distribution looks normal. But even in a really skewed skewed variable like something like weight or something that is skewed, you can see here that the skewness is relatively low. In fact, here I can see that in the population, which is the fact, the skew is 0.83. There's just a little bit of skew here, 0.36. It begins to normalize, so there's less skew. But notice that the mean and the median are very close. Here, the mean and the median are just exact, actually, as the population. I'm going to illustrate this also using larger samples of 25. When we have a larger sample of 25 over the same 10,000 samples, what's happening is even less variation. In other words, our samples are reflecting more and more truly the mean with greater confidence, as we're going to learn. We can take a look at this on this website here. And you can do this yourself. This is how you can run that simulation by clicking on Begin. This is the same setup that I had demonstrated in the prior slide. This is asking you to set up how you would like the data drawn. And I'm going to illustrate to you what happens as we draw samples from the population. In some of our data, even for this class, we have a sample of about 25. So let's run this simulation here as if we are drawing a sample of 25 something. It could be whatever. It could be top customers, for example, from a business. And what the simulation's doing here is it's representing 25 cases drawn from the population of, say, customers that I have. And then it's calculating the average and it's dropping it here. And what we can see, of course, with 25 in our sample, there is some non-normality. It looks to me like possibly some outliers here. This is what we've been looking at as we've been looking at frequencies in the data. And the question that we have is, you know, more or less the sample of 25 should reflect the population's shape, which it more or less does. But over time, a sample of 25 will definitely begin to average out. So if we kept taking multiple samples, what you'll see here is going to happen is the normal distribution is going to show up. So if I take another sample of 25, it's going to have a different distribution. This is a good example here. You can see we've looked at some of the school data that have samples of IQ scores that are really low, but most of the IQ scores are in the middle. This could be an example of that. But again, averaging it out, we see here that we have something that is around the mean. Despite this variability, when I take the mean of the sample, it does reflect the mean of the population, and that's really the point. We can continue to do this for up to however many times we want, and what we're going to see now I've run 30,000 samples of 25 is it's very tightly clustered around the actual population mean, and a tighter standard deviation because we're not seeing all the variability in the tails of the population in our samples. That's to be expected. We're only seeing some, but the importance is that we can see this clustering around the mean. So going back to this illustration is intended to help you keep that in mind, and we'll talk a little bit about this as we get into confidence intervals. So to complete this story, a population tells us a lot about the random sample that it's come from, and we can see, for example, based on our sample, we can anticipate what the population's mean and standard deviation would be. We just demonstrated that in the simulation we just ran. We were quite confident, actually, that we were seeing the population's actual mean and approximate standard deviation based on our samples. Random samples will tell us much about the population, so it works both ways. We know much about our random sample. It's telling us about the population, and the population is telling us much about our random sample. A random sample of 100 is not going to deviate sharply from the underlying population. So we can infer with confidence the population's properties, especially its mean and standard deviation. So this is the central limit theorem. Because we're now taking samples of entire means of samples. We need a different way of measuring it rather than the standard deviation itself, but it's very similar if you want to think about it as a standard deviation. We use this measure called standard error. This is how it's populated. If you know the population standard deviation, and in some rare cases we do know that nowadays about different either kinds of behavior or facts, we've sampled enough that we do know an actual population's mean and standard deviation. We can utilize that, and then this is going to be the square root of our sample size, and this is going to help us adjust for variability that we may have based on our sample size. And I'm going to illustrate the importance of this in some slides coming up. If we take multiple samples, we know that the means that we get from those samples are going to be very close to the population mean. Some will be a bit higher, some will be a bit lower, but it will take the shape of a normal distribution. We just demonstrated that in the prior slide. This is true even if the population that the samples are drawn from are not normal. We showed that with the skewed distribution. It still becomes normal. So the larger the sample size and the more samples we take, the more normal it will become. So this is really the wisdom and the insight that we have for inferential statistics. Now that might seem like a lot. Maybe that's making your head spin a bit. But here's something to ground you, because we've already seen how important this normal curve is to our understanding of statistics. And the good news is it still applies here. In other words, as we keep taking samples, random samples from a population, it will roughly cluster around the mean the way that we're expecting. 68% of all the samples are going to be within one standard error. You can think about it like a standard deviation of the population's mean, and 95% between two standard errors, and 99.7% between, that should say 3 standard errors. I'll correct that in the deck that I send to you. So the point is that we know this already. And this is what's helping us interpret a normal curve. The target population is the one in which we want to make the decisions about. And so we sample that population, and what we're able to do is interpret the statistics in our sample, hopefully based on whatever the population that's actually taken from. And so we can compare our sample and interpret the population. We can show that if a sample's mean is more than 3 standard errors, 3 standard deviations, which should be this amount right here, away from the population mean, we know that it's very rare. It's not likely taken from that population, and that's exciting. Sometimes when we find that, it's not necessarily bad news. It means that we've discovered a new population. That could mean that our drug is helping patients get well, and they no longer are appearing the way that people without getting the therapy or the drug are. They're coming from a new population, a population of well patients. And so this is good news. That's what hypothesis testing is all about. So confidence intervals express the degree of confidence that we have that we can interpret the population's, say, mean or standard deviation from our sample. It has upper and lower limits. We generally want confidence around 95%, and that's to mean that if we continue to sample the way that we are, about 95% of all the samples we would draw would fall within these bounds. So if we keep repeating an experiment over and over, we're 95% of the time we'll keep getting those results. This has a little bit of jargon or a little bit of notation. The confidence interval is expressed this way. So to get 95% confidence, we're going to be utilizing this amount of, we're going to refer to this as alpha in just a moment. This is going to be the error that we have. So we're 95% confident that every time we repeat an experiment, we'll continue to get the results that we're getting, but 5% of the time we won't. Sometimes that'll be bad news, sometimes that could be actually very exciting. So we'll see how that works. So this should look familiar. This is the same information that we've been looking at. Plus or minus 1 standard deviation, or standard error 2, and then 3 encompasses just about all of the values that we would be getting. A sample's mean is unlikely to really exactly meet the population's mean, but that's okay. We just need to have a confidence. We just saw in the simulation, sometimes a sample's mean was a little bit off to the side, one side or the other, but we kept adding them all up, and we were in fact measuring the actual population's mean. And so that's what the central limit theorem has shown us. Here's an example. There's a lot of different things that you can do with this information. I'm trying to highlight just the key ones that I want you to take away from this class of how to work with the central limit theorem and this data. The Economist magazine reports from a study of 300 subscribers that the average income is $80,000 with a standard deviation of $15,000. How close in would this real average be the real average income of all subscribers? In other words, we want 95% confidence that our mean represents the population. So this is a question that you can ask using confidence intervals. A confidence interval, as I already defined, is 1 minus some level of alpha. So if I want 95%, 1 minus 95%, alpha is going to be 0.05. So that's leaving the 5% sort of error, or times that. I'm not going to get a sample mean inside this bound of 95%. That's not necessarily always a bad thing. I'll show you why. So with an alpha of 0.05, if we keep repeating that experiment, this is the interpretation. 95% of the time, our results will continue to match the results from the population. This is what that would look like. If I need 95% of all the values that I'm sampling, these are sample means, again, 5, 25, whatever, I'm sampling over and over of the population. I'm expecting 95% of them to always fall within this bound. But that leaves 5% that are sometimes too far below or too high above. When I go and sample, that would be considered unusual or rare. In fact, it might be so rare, you'll see in a moment, it might mean that they're really a member of another population, not represented by this one. And so we know a lot about this. This should look familiar. We've already been looking at z-scores to calculate area in the tails. And I have the entire formula of that below in a note. But this 5% is basically divided up between the upper tail and the lower tail of the distribution to leave 95% in the center, just around the population's actual mean. And this is what we are theoretically doing when we're sampling. We're expecting to have our samples within this range. And if something is unusual, it's probably going to be in these tails. Now we can adjust this level of confidence. It doesn't always have to be that, but here's how we would actually fill this, this question out. Since we need 95% accuracy, that we would be within an average income of 80,000, reflecting the actual population. You can see how you would fill in the formulas yourself if you wanted to do that, and it would come out with a value of $1,697.41. And because it's on the upper end of the normal distribution and the lower end that we're accounting for effectively some variance, some error, we can have 95% confidence that it's all going to be in between those two bounds, those 2 points that we just looked at on the prior slide. So this is the amount, 81,697 and 78,302 are going to be 95% of all of the means that I would sample from this population of subscribers are likely to fall within these two amount of earnings. So that's helpful information. I'm going to expand on that. What happens if we repeat this experiment, but this time we just sample 20 subscribers instead of 300? What would that look like? Now I can still compute a 95% confidence interval. Notice I got the same mean, but this time I only have 20 subscribers, so my sample was much smaller. Well, now there's more variation in the sample. You can do the math just plugging into the formula there, but now you can notice that the error, the variance, the variability that I got in those sample means have now expanded from $4,000 to over $6,500. So I can still be 95% confident that the actual average income for all the subscribers are going to be in that range. But it's wider now than it was when I had a sample of 300. And this is the central limit theorem at work. As I get larger samples and more samples, I'm more confident, and I get a tighter range around the actual population's total earnings, in this case, average salary. But as I have fewer and take fewer sample, I'm going to have a wider range, effectively same level of confidence, but a bigger range. We can see this plotted out of what's just happened here with this example. In the first example with 300, I had a really tight range. My 95% confidence was right in this range here because I had such a big sample. And so I'm quite confident with 300 being sampled that I'm really measuring the population average of 80,000. But when I only have 20 people in my sample, now it's still a normal curve, but look what's happened to the range. There's this gap between what I could have had with 300 and what I do have with 20, because I have to account for more variability, and that was the variability that we were getting in that bigger range. So we had about a $4,000 range here and a $6,000 range here, both with 95% confidence that we're still capturing the mean of the actual population. Here's another example. How many subscribers at least should we sample to be 95% confident that the average income of all subscribers are within $5,000 of the population mean? And then I want to repeat that with 1,000. Well, again, I'm going to give you the formula here. It's more important conceptually that you're understanding what's happening. If we were to plug this in, this is the z-value we know is at 95% confidence, leaving just those 2.5 proportion in the tails, and then the rest of it just sort of falls into place. And what we can see here is that if I need a sample that will give me the number of subscribers' income within $5,000 of the population mean, I only need a sample of 35 people. But if I need to be within $1,000, very, very tight around the population's mean, I need a much bigger sample. And so you can use this formula to calculate really either way. You can look at how confident you want to be around a total amount of earnings, or you can look at it from a number that you need to sample. And this would be the interpretations there. So luckily, we don't have to keep figuring this out. Other people have looked at these tables and figured out the most commonly used confidence intervals are usually, we want to have a confidence of 90% around a population's mean, 95% or 99%. And we've already calculated the values that we typically use in z-scores in those formulas. So if you wanted to, you could go back and recalculate those things using a different confidence level. You could go back and recalculate them with a 90% confidence level using this z-score, or a 99% confidence level using this z-score. I've already done that for you with this level of confidence. And we are on what's called two-tailed. That's why we were looking at this area, and I'll explain what we can do with one-tailed in just a moment. So if by hand, here's a cookbook, so you could go back. I've just plugged the data in that we just used, but with a little bit less of the symbols of it. So if you wanted to use it as a cookbook, you could do it that way. Now, the t-distribution is something that we used for small samples. And small might be something that's less than 30. As we saw. T-distribution is very similar to the z-distribution. I'll show you that. Specific t-value depends on a new parameter called the degrees of freedom, which is functioning very similar to kind of like a variance. And then we use the sample standard deviation because we have such a small sample. We need to accommodate or utilize the information we're getting from the sample to compute the statistic. Here's how that works. There's a strong relationship between the normal curve. This is, say, the normal z curve that we would see for a z table. But what you're trying to illustrate here is that if this is the normal curve, the one at the top, with 10 and 20 degrees of freedom, it's very similar. What's happening is when it has 10 degrees of freedom, it's a bit wider, a bit fatter in sort of the sides, which is going to accommodate more variability because we're less confident, because we have there's usually a really small sample here. If we have 10 degrees of freedom, we probably only have about 11 folks in the sample. Here we'd have about 19 folks. And so there is a relationship, and as we get very large samples, the t-distribution and the z-distribution pretty much converge, and so we ended up just using the z. Luckily, the stat packages will figure this out for us, but as an illustration, if a reporter wanted to write an article on the cost of off-campus housing with a sample of 16 one-bedroom apartments around the university within a half-mile campus, the sample mean was that they have about $750 per month of average rent, standard deviation 55. What would be a 95% confidence estimate that the mean rent per month was actually reflective of that population? Well, we have to assume, of course, the population is normally distributed. We would utilize something called a table to calculate degrees of freedom. And in this case, we had actually looked at 16 apartments. So 16 minus 1 is going to give us degrees of freedom 15. We use the table to look up this value. This is very similar to either think of it as the z-score that we had utilized previously, but we're using the t-table. So it's very similar to the function of the z-score that we had used. So that's how you would utilize that table. And then we matter just plugging the information that we have in, and this is the formula for this. And we could then calculate that we're 95% confident that the mean rent per month of the population that we just sampled was this range from 720 to 779. Again, I'm illustrating this because conceptually it's important, but in our case, most of the time we're going to be utilizing a stat package to help us calculate this. But it's important to understand that even with small samples, we can still utilize that to help us interpret something about a larger population, which in this case, the population would be maybe all one-bedroom apartments that are available even in a wider area or around all universities if we wanted to find that as our population. Here is a little decision tree. If the population standard deviation is known, we're safe to use the z-score, z-tests, because we have a known case. But even if we don't know the population standard deviation, we would use the t-statistics, and that we would use the sample to effectively estimate that, and that's what that formula was doing for us. But again, the stat package is going to do that. I doubt we're going to be calculating any of these by hand. Now, when there's a lot of information here, but as you get comfortable with this and more familiar with it, you're going to see that with very limited information that you can often find in news articles about things that might mention a mean and a standard deviation, you can begin to interpret an awful lot about the population that the sample is drawn from. And it's very common to estimate things like standard deviation in a population as you become more familiar to figure some of these things out, such as the range of salaries earned and things like that. But a caution here is that we're still susceptible to social influence and bias. We often have overconfidence in our ability to estimate some things that we don't know. It's often not known, the population standard deviation, for example. We might know a mean that we want to use, or we have information on our sample, we're trying to apply it to a whole population. So these are just some cautions. 84% of Frenchmen estimate that they're above average levers, 82% drivers say that they're in the top 30 of safe drivers. Well, that can't be. Business owners think that their business are going to succeed, but their competitors will fail. And shockingly, some faculty members believe a lot more than they should that they're in the top 25 in teaching ability. Of course, that could be one I should really be mindful of. So the point is that overconfidence is we're very susceptible, and actually as we become more familiar with something technical like statistics, we can often suffer from it more. So be mindful of that and proceed with caution. I know it's a lot today, you don't feel that confident, but as you reflect on the information, you might be tempted to do that. So the takeaway for it today, we looked at how confidence intervals can help us determine a range of values that our sample actually represents the population. And so we would be able to repeat our sample. We can be 95% confident that our results will reflect the population within some range. And that's really powerful information. We'll see that in just a moment with SPSS. If we know a population standard deviation and a range we want to be within, confidence intervals help us estimate a sample size and other kinds of useful things. And lastly, even when relatively small samples, we can still estimate values and that we expect with confidence. And that makes it very powerful. Central limit theorem at work there so that we can interpret statistics and make better inferences about things that we would expect.